Good evening, ladies and gentlemen. We are Group 4, and we will be presenting video super resolution using deep learning techniques. This is our team. I'm here with Marwa Sulaiman, Muhammad Naggar, Isra Fahmi, Dareen Hussein, and Zahra Shahabuddin, and myself, Muhammad Barakat. In our presentation, we'll go through our hypothesis and contribution, our proposed architecture, the experiments we've done and their results, our discussion and final remarks. So let us begin by describing what we've been doing through the last 2 semesters. So we've been studying video super resolution, which is the process of enhancing the quality of videos. So at the moment, there are many neural network models for VSR. However, there exists many trade-offs between these models. So we proposed a new model to minimize the trade-offs between the different existing models. Then we've performed many experiments and we've compared them with the existing models. So in our experiment, we'll be explaining all the process in extreme details, and we will conclude with a final conclusion and our remarks. So let us begin by a brief introduction about VSR and our conclusion and our hypothesis. So video super resolution, or VSR, is the process of generating high resolution video from a low resolution video. So a video is essentially a sequence of frames. So VSR, or video super resolution, can be thought of image super resolution applied to each frame in a video. However, in video super resolution, the temporal dimension needs to be taken into consideration. The relationship between each frame in a video to the successive or the preceding frames needs to be taken into consideration. And this is the main difference between video super resolution and image super resolution. So why do we do VSR, or video super resolution? Because it has many extensive applications in real life. It can be used in healthcare in generating high resolution images, and in entertainment in generating in high definition television, and in remote sensing and surveillance. Current VSR models have many issues and challenges in them. First of all, there is a huge need for a lightweight super resolution model, because many of the existing models are heavyweight and they take a long inference time for frames. So there is a need for a lightweight super resolution model. Also, there needs more effective scene change algorithms to take the temporal dimension into consideration, as well as the need for more reasonable evaluation criteria for the quality of videos. This leads us to our hypothesis. So the main issue is that current models for VSR are hard to deploy because of the heavy weight of the models and the trade-off between the weight of the models, the quality of the video, and the natural flow of the generated video. This is why we are proposing a model which integrates 2 of the state-of-the-art models. It combines the generator of TicoGAN with the discriminator of RBPN, which are 2 models, to improve the temporal coherence and maintain the quality of the generated video. Now, part of the training occurs in the discriminator, which keeps the model size constant and enhances the quality of the video. Now, Zahra will continue with the proposed architecture.
Okay, so for the proposed architecture, we'll go through the base models, which are the generators and the discriminator, the loss functions, and the data set. Starting by the base models, we're having 2 main base models, the TicoGAN, which stands for Temporal Coherent GAN, and the RBPN, which stands for Recurrent Back Projection Network. Starting by the TicoGAN is a generative adversarial network, which means it contains a generator and a discriminator. For the generator, it generates the high resolution frames from an input of low resolution frames. Then the generator takes the high resolution frames and feeds them into a motion estimation module. After that, the generator takes the low resolution frames and the previously estimated high resolution frames by means of concatenation to generate the high resolution frames. It also the warping is done on the previous high resolution frames to get the newly generated high resolution frames. And regarding the discriminator, which will be our focus in this project, the discriminator, it compares the high resolution frames with the ground truth. Next, okay. For the ground truth, also the discriminator proposed a new ping-pong loss functions. This loss function is to get the highly low temporal flow between the low resolution image and the high resolution generated images. For this discriminator, the discriminator receives and concatenates triplets of frames. Also, it guides the generator to learn from the high resolution frame and the low resolution frames. Also, the generator the discriminator, penalize the generator if the generated frames contain artifacts or unrealistic. And finally, is a orbit frames is to classify the unrealistic and unnatural temporal flows. Then for the generator, which we will use in our model, it's as I mentioned, it's the recurrent back projection network. The basic concept behind back projection is to iteratively calculate the residual image as a reconstruction error between the target image and a set of neighboring frames, which in this case, they used 6 neighboring frames. And we will mention it later in our model. We reduced the number of neighboring frames. Also, it exploits the temporal relationship between adjacent frames. Furthermore, the RBBN is a superior results by combining the benefits of the original multi-image super resolution and the back projection image. Okay, so for the generator here, it has the 3 main features: the feature extraction module, the projection module, and the reconstruction module. Starting by the feature extraction module, it has 2 main rules. One is to extract the features from the target frame, and the other is to extract the features from the concatenation of target frame and neighboring frame. To feed them into a model to get the high resolution image. And the second module is the projection module. It consists of an encoder and a decoder. And finally, for the reconstruction module, it consists of a residual blocks and single image super resolution and multiple image super resolution to produce the high resolution frames. So this will be used as our generator in the model. Next slide. Okay, so for the architecture here, as I mentioned, the generator will be used from the RBBN network, while the discriminator will be used from the TicoGAN to make sure that we're having a good accuracy and a good temporal flow. And now Darine will continue with these functions.
Next slide. So regarding our loss functions, we have been dealing with 5 main loss functions. The first one is the standard GAN loss function, or what is commonly known as the min-max function. Its main aim is the generator tries to minimize the function while the discriminator tries to maximize it. The second loss function is the pixel loss function. It deals with the pixels by trying to minimize the absolute error between them. Then the third function is the warping function, which deals with the neighborhood frames and tries to minimize the error between them. Then the perceptual or feature loss function, it compares the semantic content of the practical video, which defined using the adversarial network. Then finally, the newly introduced ping-pong loss function, which reduce long-term temporal details by trying to reduce artifacts and at the same time keeping the details. Next slide. So what we are aiming here is to maintain, as Barakat said, high accuracy while enhancing the spatio-temporal coherence. So that's why we are depending on RBBN model as a generator for our GAN network, as it record a high state-of-the-art accuracy, and using TicoGAN as our discriminator as it add temporal coherence. So while we were setting our environment, we needed to set specific things. We used the NVIDIA, the Alienware with 1 GPU. It uses GeForce RTX 390, and at the same time uses the NVIDIA driver. But when we're trying to run our base models, we found that they needed a lot of dependencies and libraries to be introduced. So that's why we have been installing this list of dependencies. Now, regarding our data set, we have used the main data set that is used in VSR models. Some are for testing and others for training. We have used VIT4 and the famous TOS3 for testing, and VIMU90K and VIMU-TicoGAN for training. Now, regarding the evaluation criteria, the usual criterion for evaluating the quality of super resolution is through the peak to signal ratio, commonly known as PSNR. The main value of PSNR is that measured the ratio between the maximum possible power of an image and the power of the corrupting noise that affect the quality of its representation. However, its value only is not able to reflect the video quality from a human perception. That is, even if the PSNR value is high, that doesn't mean that it's appealing for humans. That's why we have used another qualities, that assessment matrix, like LTIPS and TOF. LPIPS, which stands for Learned Perceptual Image Patch Similarity. It evaluates the similarity between image.
آخر دقيقة please نرافق. آخر دقيقة.
It evaluates the similarity between image patches. The matrix is close to the subjective evaluation of human eyes. Therefore, LPIPS is more accurate than the first matrix. Highers mean more different, while lowers mean more similar. And finally, TOF, which measured the pixel-wise difference of motion from estimated sequences of frames. So that's why we have been comparing the results from the base models presented in the original papers. And as can be seen, PSNR value is preferred higher, and that's why it was obtained by RBPN due to its highly structured architecture, while LPIPS and TOF got better results in TICOGAN as it's more visually appealing. Now my colleague Nagar will continue with our experiments.
Okay, so here you can see briefly our experiment sequence. And we started by training TICOGAN and RBPN, which are our base models. Then we integrated them. And finally, we tested again RBPN, but with different settings in order to match our configurations for RBPGAN, which is our model. Okay, so again, our experiment one, we started by training RBPN, and we faced a major problem while training RBPN, which was that we couldn't fit this whole model inside our GPUs because it's relatively a big model. So we solved this problem by decreasing the number of frames, which of course affected the accuracy of the model. And we also decreased the batch size. And we trained the model for 150 epochs as suggested by the paper. Next, we trained TICOGAN, and we, with a slight modification of training it on 2 GPUs instead of 1, as the code that was published on GitHub was utilizing only 1 GPU. So after this slight modification, we reduced the training time from 9 days to around 1.5 days. And we also produced a very small inference time relative to the other model, which is 40 milliframes per second. Then we integrated the 2 models, and we did that basically by removing the generator of TICOGAN and converting the RBPN model from a feed-forward network to a generator network. And we basically integrated them together, and we modified them in order to match our data set. Next, Mara will continue with the detailed experiments that we made.
So after we integrated our model, which is the generator as RBPN and the discriminator of TICOGAN, so the model is now ready for some experiments to do. So the first experiment is that we used all the losses we mentioned, which are the ping pong loss, the pixel, the feature, warping, and GAN loss, of course. We used 4 neighbor frames per each frame. So to remind you, the neighbor frames are the frames that are just before and after the frame we are interested to generate high resolution for. And also, I want to mention that the number of neighbors affect the size of the model, because as we mentioned in the RBPN, each neighbor is fed into like a block of the network. So increasing the number of neighbors actually increases the size of the model. So we tried as much as we can to minimize this amount of neighbors while maintaining good accuracy. We also used the Vimeo TICOGAN dataset, and the training time for this experiment took around 3.5 days. The second experiment, we removed the ping pong loss to monitor its effect, and the effect of removing it. So we used the L1 feature loss, warping loss, and GAN loss, which are the losses except the ping pong. And we used 3 neighbor frames per each frame.
and training took around 3 days, and training on the same data set. And we will compare all of these, or the results of all these experiments later. The third experiment is that we did some fine tuning. We trained part of the generator and then loaded it. So the training continues from this point. And now I'll compare the result of the 3 experiments. Oh, sorry, the 5th experiment was that we trained the RBBN, which is the base model for the generator, but with our settings, so to have a fair comparison. So we use the same neighbor frames and the same crop size and the same settings we used for training our experiments. So here you can see a table comparing the 3 experiments we did and with their values to determine the best one in order to compare them with the base models. So as you can see here, experiment 2 got the best accuracies for the PSNR, which represents the accuracy or the quality of the videos, and the LPIPS, and temporal, and TOF, which represent the natural flow and the smoothness of the video. So we'll use experiment 2 to compare with the models. So here, all the comparisons are made on the VIT4 dataset. And you can see here that our model actually achieves the highest accuracy in terms of LPIPS, which corresponds to the natural and smoothness of the video. So it's surpassed the state-of-the-art model in models in this metric, and we are very proud of that. And regarding the PSNR, it also achieves good quality, comparing it to both models. Now Isra will continue with the discussion and the conclusion.
So to put all this into graphs, we actually created 2 graphs, one for the temporal coherence and the other for accuracy. And please note that the temporal coherence, the less is the better. So our graph here for RBBGAN in orange, that showed that we conducted very good results according to the state of the art. Also, according to the accuracy, we achieved slightly better accuracies than TICOGAN. However, we couldn't exceed our BBN because of the reduced model. Now moving on to the best part, you can see that our high resolution output here on the right and the low resolution input on the left. And we conducted this on experiment 4.2 and on VIT4 test set. This is a closer look to get a better picture of our experiment. You can see that on the left, there are more fine details and more clarity. Yes, and this is our test set. We created this ourselves, and we also made sure that it has scenario change. And also to get a better sense of it, there is a closer look here. Yeah, so you can see that the faces now are more clear and no blurring effect is obvious, and it is distinct, and all the lines are fine. Also, the chair here are more clear. You can see the lines and it is more obvious and distinct. Now to the final remarks. We actually faced some challenges. Yeah. So the first one is that we needed more powerful computational resources to conduct our test because we used GAN networks. And this was one of the challenges. The second one is that we've introduced more or less suboptimal details when cases have more details or more artifacts. And to solve this problem, we actually recommend using different downsampling techniques that introduce more generality and introduce more domains into the test set. And also we recommend using or training on a model that has more faces and text. So in conclusion, we can say that we are proud that we achieved our hypothesis to find the middle ground that actually exceeds the state of the art in regard to temporal coherence. And we also increased the accuracy slightly with reduced models. So as we mentioned, our BBN it was inspiring for the accuracy, and TICOGAN was inspiring for the coherence. And here's our RBBGAN model that has the best in both worlds. And regarding our outcome, we now finalized draft 2, and we are about to finalize our paper to be submitted to the ICMLA conference, hopefully. And finally, we would like to acknowledge Dr. Sharif Salama, our thesis director, and also our direct supervisor, Dr. Mustafa Yusuf and Dr. Hisham Arai. And also thank you all for your attending and for your time. And that's it.